Welcome to this NPTEL course on Dynamics and Control of Mechanical Systems. My name is Ashitava Ghoshal. I am a professor in the Department of Mechanical Engineering and in the Center for Product Design and Manufacturing and Robert Bosch Center for Cyber Physical Systems, Indian Institute of Science, Bangalore. In this course, we will start with the representation of rigid bodies in 3D space. The content for this week, we will first introduce mechanical systems and their various components. Then in lecture 2, we will look at position and orientation of a rigid body in 3D space. And then in lecture 3, we'll look at homogeneous transformation, where a rigid body can do both translation and orientation. The field of mechanical engineering contains various subfields. So for example, you can have thermal systems, fluid mechanics, solid mechanics, materials, design and manufacturing. In this course, we will look at mechanical systems. Mechanical systems on their own contains the study of mechanisms, actuators, sensors and computers. So for example, this picture here shows a 4-bar mechanism which is used to actuate or move the fingers of a gripper, which is used in robots. To rotate some of the actuators, we have this DC servo motor, and the DC servo motor on its own contains many elements. So for example, we have this shaft, and to measure the rotation of this shaft, we have what are called as encoders. So this is a picture of an optical encoder where we have some pairs of light emitters and diodes, and we can measure the rotation of the shaft by finding out how the light beams are intercepted by this rotating disk. We also have computers in in mechanical systems. The computers are used to measure, to do some I/O, and to do some software and computations. Mechanical system basically consists of 3 areas of study. We have kinematics, dynamics and control. In kinematics, we can also have particle kinematics, where you consider the element as a point mass. Then we also have rigid body kinematics, where we look at both position and orientation of a rigid body. Several such rigid bodies make up what is called as multi-body kinematics, and multi-body kinematics leads to this idea of dynamics. So in kinematics, we do not worry about the causes of the motion, whereas in dynamics, we look at how the motion is caused. And the goal in dynamics is to derive the equations of motion. Okay, they are ordinary differential equations most of the time, and we will deal with ordinary differential equations. A natural progression from the equations of motion is control. So every mechanical system has its own inherent dynamics. So when a force or a moment acts on the mechanical system, the trajectory or the motion of the mechanical system is defined. However, we would like to have a desired motion of the mechanical system, and this is the area of control. There are 2 main ways of doing control. One of them is called the classical methods, where we look at what are called as root locus and frequency domain and so on. And then there is also state space method. So here are 3 examples of mechanical systems. I will show you them, and these are short videos. So first is this, what is called as a sun tracking system. Basically, there are 2 mirrors which track the sun, and then they focus the incident beam onto a receiver. This is a picture of a quadruped which is moving around. Each leg of the quadruped actually contains 2 rotary joints, and there are 2 motors. So here it is shown how the tip of the quadruped, the end of the leg, is moving up and down. So a study of kinematics, dynamics and control allows us to analyze and then design systems like this quadruped or this simple 2-hour motion or even this sun tracker. Kinematics on its own consists of or looks at the study of motion of rigid bodies or multiple rigid bodies without considering the cause. So what do we study? We look at basically the geometry of the motion. So the path traced by a point, or maybe what is the extent of the motion of the point or the rigid body, and so on. So the main concepts in kinematics are position and orientation of a rigid body in 3D space, concept of degrees of freedom and constraints, linear and angular velocity of the rigid body, and linear and angular acceleration. The rigid bodies are often connected by joints. So when you have rigid bodies connected by joints, then they move or they have different degrees of freedom. So we will look at this concept of degrees of freedom of a set of rigid bodies connected by joints and the constraints which the joint impose. So there are different kinds of constraints. One of them is called holonomic and the second one is non-holonomic. We'll look at these in more detail in this course. The one classical way of looking at kinematics is what is called as particle kinematics. We assume that it is a point mass and then we study position, velocity and acceleration of this point mass. In dynamics, we look at the motion of the rigid body or connected set of rigid bodies due to the external forces and or moments. So in this case, we have to study or consider the mass and inertia of the rigid body. The motion of the rigid body or the connected set of rigid bodies can be described by ordinary differential equations, also called the equations of motion. There are several ways and methods to derive the equation of motion. The common ones are called Newton-Euler or Lagrangian, and then there is a Keynes method. In Newton-Euler, we have this concept of free body diagram. We also use Newton's law and Euler's equation of motion. In the Lagrangian formulation, we find the kinetic and potential energy, and this is an energy-based approach. In Keynes formulation, there is this use of so-called generalized coordinates, and they have this concept of active and inertia forces. We will not look at Keynes formulation in this course in detail in this course. Each formulation has its own advantages and disadvantages. And finally, in dynamics, we also need to look at how to solve the equations of motion. Most of the time, we will be doing numerical solution of the ordinary differential equations of equations. In control, we have basically a desired motion of a mechanical system. Okay, so the real or physical system does not achieve the desired motion due to several reasons. One of them is the external disturbance. So the goal of control is to make the mechanical system follow a desired motion accurately. So the important words are follow and accurately. So we will look at how much close we can follow a desired motion to what accuracy. And more importantly, in spite of external disturbances and internal parameter changes. So the goal of control is also to minimize the error between the desired and actual or measured motion. And to achieve this, we use this important notion of feedback. Feedback requires the use of sensors to measure actual motion and a control scheme. So most of the time we will use linear control schemes because this linear control scheme is very well known and studied. Okay, and it's also a basis for advanced nonlinear control schemes. So we will not look at nonlinear control schemes in this course. The two main ways which we look at control is one is called state space methods and the other one is called classical control. So classical control consists of root locus, Bode plots and other frequency domain approaches. We will not look at in too much detail the frequency domain approaches. Before we get in depth into this course, let us first look at a few definitions and notations which will be used throughout this course. So we will denote scalars using lower and uppercase symbols. So for example, small x can denote the x coordinate, theta will denote the rotation angle, m can denote the mass of a rigid body. Vectors will be denoted by boldface symbols with a leading superscript. Vectors are always with respect to a coordinate system. So we will define a coordinate system little later, but vectors are always with respect to a coordinate system. And for example, this quantity A, boldface R and C, it locates the center of mass of a rigid body with respect to the coordinate system A. So the leading superscript here denotes the reference coordinate system. Okay, and R is a vector, so it's a position vector, and we will see later that position vector can be determined or represented by three scalars. So a vector will sometimes be also denoted in this form. Here A denotes the reference coordinate system, and x, y, z are the components of a vector. So here this t corresponds, or it shows that it is a column vector. So basically this is the location of a point P with Cartesian coordinates x, y, z with respect to A. We also need to distinguish normal vectors with unit vectors. So an unit vector has a magnitude 1. So in this example, capital X, boldface X with a hat denotes a unit vector. So the magnitude of this unit vector is 1, and in the coordinate system A, the XA or the XA unit vector in its own coordinate system is given by 1, 0, 0. A matrix is a symbol within square brackets. Okay, so with the superscript and a subscript. So for example, ABR denotes the rotation matrix of a rigid body B or a coordinate system B with respect to a reference coordinate system A. Okay, so in any rotation matrix, okay, this superscript denotes the reference coordinate. A is the reference and B is the rigid body with and we say that this matrix ABR denotes the rotation of rigid body B with respect to A. Okay. Sometimes we need to represent a vector as a skew symmetric matrix. Okay. So for example, this vector AR, R is boldface, which means it's a vector with respect to the A coordinate system, with components x, y, z can be written in this form. Okay, so this is a square bracket AR to basically denote that it is actually a matrix, a vector represented as a matrix, and this will be a skew symmetric matrix. So from linear algebra, we know a skew symmetric matrix is one which has the diagonal elements as 0, and this x, y, z will be arranged in this form. So the second element is minus z, the third element is y, and since it is skew symmetric, this will be plus z, and this is minus x, and this is again minus y and x. So we will see later this matrix, when you multiply by a vector, also denotes the cross product of one vector with the second vector. So let's continue. So in this picture, I show a rigid body. So this is odd looking shape. It represents a rigid body in 3D space. So now in this rigid body, there are several important things which are of interest. One is that there is a coordinate system XA, YA, and ZA. So remember, X with a hat denotes a unit vector. A denotes the fact that it is associated with this coordinate system A. We also have an origin OA. Okay, so every coordinate system must have three things. One is a set of unit vectors X, Y, and Z, and origin, and also you have to tell whether it is a reference and a label. Okay, so we need to make sure that this label tells you that this is the A coordinate system. Likewise, in this rigid body, I can have another coordinate system which is xb, yb, zb. In this instance, the origin of the two coordinate system OA and OB are shown at the same place. Okay, so sometimes we see these hash lines. So this means that the A coordinate system is fixed. We can also have another set of hash lines which is attached to the rigid body. So in this figure, what it means is this A coordinate system is in some sense like fixed in space, whereas the B coordinate system is attached to the rigid body B. So as I said, the coordinate system is denoted by symbol inside this curly brackets. The coordinate system A is denoted by curly bracket A. A is defined by a right-handed set of unit vectors xa, ya, za and an origin OA. So there will be many such coordinate systems for several rigid bodies. So we will be labeling each rigid body in this way. So you can have A, B, C and so on. A vector in this coordinate system, say for example with respect to the B coordinate system, as can be expressed in another coordinate system. So this is very well known from basic mechanics that if you have a vector in the A coordinate system and you have another vector in the B coordinate system, they are given in terms of by pre-multiplying BR with respect to a rotation matrix ABR. Okay, so just to keep track, this notation is very useful. So for example, you can think of this B and B cancelling out. So we are left with A and this vector R, which is same as here AR. The rotation matrix ABR gives, we will see very soon, it gives the orientation of this rigid body B with respect to another coordinate system or with respect to a reference coordinate system A. So let us continue with definitions and notations used in this course. So the dot product of two vectors AR1 and AR2 is defined as the magnitude of AR1, AR2 into cos theta, where theta is the angle between the two vectors. The dot product of two vectors is always a scalar. The other important thing in dot product, or for that matter in any vector operation between two or more vectors, all the vectors must be in the same coordinate system. So it should be A here and A here. So it doesn't make any sense to do AR1 dot BR2. Okay. The cross product of two vectors AR1 and AR2 is denoted by the symbol cross, is defined as the magnitude of AR1, magnitude of AR2 into sine theta, where theta is the angle between these two vectors. The cross product of two vectors is also a vector. Okay, and the vector is always normal to AR1 and AR2, and the vector normal to AR1 and AR2 is obtained by the right hand rule. So AR1 is one set of fingers and AR2 is the other one, and the normal is along the thumb, the usual way we find cross product between two vectors and using the right hand rule. The cross product can also be viewed as a skew symmetric matrix. So for example, this vector A omega cross AR can be also written as this matrix A omega in multiplying AR. Okay, where A omega is the skew symmetric matrix which was introduced in the last slide. It has 0 in the diagonal terms and the off diagonal terms are omega z and minus omega z, omega y and minus omega y, and minus omega x and omega x. Okay. So the cross product of A omega cross AR can be written as this matrix multiplying x, y, z, and again this t implies it's a column vector, can be obtained as omega y z minus omega z into y. So this is the x component, omega z into x minus omega x z, this is the y component, and omega x y minus omega x. Okay, and this is also a column vector. This again, remember, t denotes it's a transpose or the column vector. The derivative of a vector AR denoted by AR dot is nothing but the derivative of each of its components. So it is x dot, y dot, z dot if AR was x, y, and z. The derivative of a matrix is the derivative of each element in the matrix. So we will need to use derivative of a matrix later on. Before we go into this module, a quick word about the numerical simulations in this and other modules. MATLAB has been extensively used for numerical simulation and obtaining numerical results. All modules of MATLAB are available to participants of NPTEL. A very basic video of MATLAB and how to use it has been created by the TA Soumyakanti Mahapatra and is freely available at this website. Please go to the website and you can explore and see what all are the material which has been put there. The link contains the introductory video, almost all programs in MATLAB used to generate the numerical simulations, and animations and other useful documents. Videos of other software tools used in this course, such as Adams, and created by other TAs for this course, Mr. Pramod Pal and Yogesh Pratap Singh, are also available at the above link.